All right, we are continuing with photonic structure of the nucleon. Switching gears a little bit, let's have US Mets from Temple University, who is a world-leading expert also dimensional structure of nucleon. He will tell us about multi-dimensional pattern structure of patterns. What was yours?
So yeah, it's actually a pleasure for me to have the opportunity to be here and give a couple of lectures. I know that you are among the people who will, in one way or another, contribute to EIC science over the next years. That is very important, and I hope I can. Some of the stuff that I talk about is perhaps for some of you maybe a little boring, but I hope that everyone actually takes something away from this lecture today and tomorrow. All right, so we want to study pattern structure of hadrons, of the nucleon, to be more specific. And you had several lectures. You came here with a background you know very well. If we talk about that, we have in mind high energy collisions. And that means, by definition, we have particles that have very high momentum. And whenever you have such a situation, it is convenient to use these light cone variables. Well, maybe I can. So the light cone variables here, and the reason is the following. Imagine we have a nucleon which has a large third component of momentum, then the plus momentum of that nucleon, basically indicated here, is very large. And in comparison, the minus component is negligibly small. So we basically can typically neglect one of the components of a four vector, at least one. And so now we are looking at a parton inside this hadron here, and that has a plus momentum K plus, which we say is a fraction X times the plus momentum of the hadron. That parton also has a transverse momentum K perp, and it has a transverse position. And that basically already defines the outline of the two lectures here. We will have a short discussion, well, some discussion on parton distributions, which I think to some extent is complementary to what Pavel has been talking about earlier today. Parton distribution functions by definition contain information about X. Transverse momentum dependent parton distributions, or TMDs, contain information about X and K perp. Generalized parton distributions contain information about X and B perp. And finally, the most general objects, generalized TMDs, or GTMDs for short, contain information about X, K perp, and B perp. Don't forget this. This is a big picture. And so before I continue, so let me ask, who of you is working in stuff going beyond 1D? Don't be shy. Seems very few, actually, surprisingly few. Definitely less than 50%. All right, so as I wrote on the previous slide, what we can do here is just bits and pieces. And I give you here, by no means a complete list of literature. If you want to study that stuff more, there's a nice short introduction by Marcus Steele about 10 years ago. This is actually an article in a special volume of a European Physics Journal A, where you have a bunch of articles dealing with the 3D structure of hadrons. Last year, so let me make a little bit advertisement for own work. We wrote a somewhat longer introduction to the field. Then here we have two documents focusing on TMDs, in particular this TMD handbook. It's a very comprehensive document with a lot of technical details. This document here focuses on GPDs. And finally, if you're interested in this stuff in relation with the electron-ion collider, I refer you to the EIC white paper and the EIC yellow report. All right, so let me start with something that you were familiar with before coming here. You heard much more about this in previous lectures. But to set up the notation, I want to start also with inclusive deep inelastic scattering, DAS, and the 1D imaging, so electron scattering of a nucleon. The interaction takes place here through the exchange of a virtual photon. The photon hits a quark, and then the, let's say, struck quark together with the remnants of the nucleon form the inclusive system X. And by definition, the only particle which is detected is a scattered electron. That's what defines inclusive deep inelastic scattering. The unpolarized cross-section is fully determined by two variables, capital Q squared, which is minus 4 momentum of that virtual photon squared, which is positive. And the reason why people use that here is that whenever you have electron scattering, regardless of the final state, be it the fully inclusive final state or an exclusive final state, semi-inclusive final state, the lowercase q squared is always negative, and we introduce that. Then we have x pRkn as q squared divided by 2p dot q, p being the full momentum of that nucleon here. And then there's another variable y, which, however, is not independent. It's q squared over xp, s, where s is the squared center of mass energy for the process. Now, if we look at the cross-section in the well-known Parton model, we calculate it in the following way. We calculate a partonic cross-section for electron-quark scattering. This is this beast here. We multiply it with a probability density to finding a parton with momentum fraction x of quark flavor q. We integrate over all possible values of x from 0 to 1, and we sum over quarks. That's it. And take a look here at this partonic cross-section. The only thing I want to focus on here is on this delta function, and that is pretty remarkable, which tells you that this momentum fraction x of this quark, which is seen by the virtual photon, agrees with x pRkn. This is a highly non-trivial result. We keep in mind that no one has ever seen a quark in a detector. And if you want to probe quarks at momentum fraction, let's say 0.3, you can do that, even though you don't see it directly, by tuning your experiment such that x pRkn is about 0.3. This simple relation here gets spoiled or distorted once you go to higher order corrections, but in the first approximation, this is still correct. So now, this is the scattering amplitude. We square the amplitude, and you know, if you square the scattering amplitude, you get a cross-section. So this is a so-called cut diagram representation of the cross-section. This cut here indicates that if you do a calculation, you put all the particles on shell which cross the cut here. And in the following, we will focus on this lower part of the diagram. Incoming nucleon, outgoing nucleon, and these two quark legs. When we talk about PDFs, TMDs, GPDs, GTMDs, we always talk about this same object. The only things that change is the kinematics that we use for these particles. So that is basically, so we will now spend more time on this guy. All right, so let me go slowly here because this stuff here is relevant for all the 4 types of Parton distributions that I mentioned in the beginning. The momentum of the incoming line here is lowercase p, outgoing line is p prime. I'm introducing this average p here, and the momentum transfer delta is p prime minus p, and then you can readily verify that lowercase p is p minus delta over 2 and p prime is p plus delta over 2. K is the average momentum of these quark lines here. And now in field theory, this object here is defined in this way. These 2 quark legs here correspond to these 2 quark field operators. They are sitting at different space-time points, z over 2 minus z over 2. And because of that, I need a Wilson line to make sure that this object is color gauge invariant.
Is defined on phase space. The inner product is of relativistic dot product.
Where?
K dot CIB.
K dot C.
In the
Yes, yeah. That is it's a scalar product for vectors.
Okay, gotcha.
Yes, yeah.
Thank you.
So these are Dirac spinors. So I and J are Dirac indices. So this object here is a 4x4 matrix in Dirac space. And this operator is evaluated between the incoming hadron and the outgoing hadron. We take the Fourier transform, and the result depends on this average momentum K. And of course, it depends on P and N. Now, to define parton distributions, we cannot use the 4x4 matrix in Dirac space because a parton distribution is a number. So we take this matrix and take a trace with an a priori arbitrary gamma matrix, which I call here gamma. This is now a number. Again, this up to here, this discussion applies to all four types of parton distributions that we mentioned. And now in the next step, I become specific and say, what do we do in order to get PDFs? In particular, what we do is we say for PDFs, the momentum transfer is 0. And you can easily see that here because in the PDF case, we have the square of that diagram, meaning that the momentum of this line and that line is just the same. So there is no momentum transfer. So delta is 0. K plus, as we said before, we call this x times P plus. And the non-trivial integrations that we have here is upon K minus and K per. And then you can readily convince yourself you get from this object here, if you do this integration and the delta function to this, let me give you just one piece of input here. And again, don't be scared by these equations here. It's not that complicated, in fact. If we integrate over K minus, this object, the only K minus dependence is in the exponential. And if you carry out that integral, then you get a delta function in Z plus, and you can carry out the C plus integral, and C plus is put to 0. The same applies for K perp integral, and Z perp is put to 0. At the end of the day, the correlator that we use to define PDFs is a light cone correlation function, where these two quark fields are just separated along the light cone in my convention here, the C minus direction. And so now we are basically ready to define parton distributions. If we want to do it for a spin 1/2 hadron, like the nucleon, we also have to pay attention to the spin. One way of describing the spin is such a spin 4 vector, which is specified through helicity, potential helicity of the nucleon, and the potential transverse spin vector. This S satisfies these constraints here. It's not so important for the following. And here we are. These are what we call the leading twist or leading quark PDFs for a spin 1/2 hadron. In the case of the unpolarized PDF, which I call F1Q, the gamma matrix between the two quark fields is gamma plus. In the case of the helicity PDF G1, we use gamma plus gamma 5, and for the transversity PDF, it's I sigma I plus gamma 5, where I is a transverse index. Interpretation is F1 is a density of unpolarized quarks in an unpolarized nucleon. G1 is the density of longitudinally polarized quarks in a longitudinally polarized nucleon, and H1 the density of transversely polarized quarks in a transversely polarized nucleon. Now, when you write this down here, and also for other sorts of parton distributions, the general structure of this correlator here follows from parity, hermiticity, and time reversal. I'm not showing this here in detail. More specifically, in this case, parity determines that all these three traces here are just given by exactly one structure. Hermiticity leads to the fact that these functions are real value. And in this case, time reversal actually does not impose any constraint. That is different if we move on, for instance, to PMDs. The other thing, and I know you have been talking about that as well, when you try to calculate an object like that, which you can do in principle in perturbation theory, you run into ultraviolet. Whenever you have this, you have to normalize. So these Parton distributions depend on the renormalization scheme and therefore also on the renormalization scale, which people typically denote as mu, and I have suppressed it. So let me elaborate a little more on the interpretation of these functions. And for this, I'm using here these projection operators onto quark states with a definite helicity or chirality. If we neglect masses, these two are actually exactly the same. So if lambda here is +1, we are projecting onto a positive helicity or chirality state. If it's -1, on a negative helicity state. And you can readily verify that these operators here satisfy the usual properties of a projection operator. If I can now express, for instance, the operator for F1, this psi bar gamma plus psi, in terms of these fields which have a positive or negative helicity. And what you find here is psi bar plus gamma plus psi plus and psi bar minus gamma plus psi minus. So F1 actually describes the sum of two densities. In one case, helicity is plus, and the other case is minus. Sometimes people also call this the spin average PDF. If we do the same thing now for psi bar gamma plus gamma 5 in the helicity case, we get the same terms here, but with a minus. So what we call the helicity PDF is actually not just a single density, but it is a difference of two densities. And because of that, it can become negative. And in fact, depending on the quark flavor, we know that it is negative. And finally, here, this weird thing of transversity, which often confuses students. This describes the difference of the two densities with a transverse quark polarization. If you do your quantum mechanics and you work spin eigenstates, and let's say you have an eigenstate of sigma x, which would be a transverse direction here, you can write this as a linear combination of eigenstates of sigma z. In the same way, I can actually express these transverse quark polarization states in terms of these helicity states. And then if you work this out, you get all at a sudden a psi bar plus, and here psi minus, and here psi bar minus, and here psi plus. In contrast to these cases here, where this helicity is the same, here it is different. And that's why we call this object chiral odd. And why does this actually cause a problem? Well, we can readily see this here. So these two psi fields, remember, represent these two quark legs. If we now have the transversity situation, if this here is a plus leg, then this here is necessarily minus and vice versa. However, what happens here, if this is plus, then we have an interaction with a photon, but the photon coupling does not change the helicity or chirality of a fermion. Any interactions in the standard model don't change the helicity of massless particles, and we neglect masses here. So if this is plus, it remains plus here, and again it remains plus, but this is supposed to be minus, and therefore this transition is actually forbidden. That's, in a nutshell, the reason why the transversity decouples from this simple process of inclusive deep inelastic scattering, and that is a very deep reason why the information that we have today about this third PDF is just poor compared to the other two. And so what you have to do is you have to come up with a more complicated process where you have another chiral odd piece showing up, and that is just in general not as easy as the inclusive deals. So I will not go through everything here, but well, most of the points. If you really want to drive home this discussion about the density interpretation, you have actually to express these quark fields in light from quantization. And then you can show that you end up literally with a number operator sandwiched between the hadronic states. I didn't write this down here. Then another thing which you probably have already spoken about here at the school, or you knew before, once you include radiative corrections, the density interpretation is spoiled. So this is pretty obvious because if we have a scheme dependence, the scheme dependence basically means I have different ways of, I have to subtract a pole that is defined that I have to subtract, but then the scheme dependence is about subtraction of different finite terms. And depending on the scheme, you can basically get anything. So this renormalization process spoils the strict density interpretation of these Parton distributions. Still, talking or thinking of them in terms of densities is a good guiding principle. The other remark I want to make here is these polarized densities, we can actually consider as describing the strengths of certain spin-spin correlations. For this, I take here the projection that we had for the helicity case, and I multiply with, let's say, the helicity of the quark, and then on the right-hand side, I get the product of the helicity of the quark and the helicity of the nucleon, and therefore we can say this G1 describes the strengths of this particular spin-spin correlation. And the same thing applies in the case of the transversity. Just replace helicity by transverse polarization of both the target quark and the quark. Let me skip over that here. I don't actually need it for the following. And before moving on, let me just in passing say, so far the discussion was about quarks. Of course, we have also unpolarized gluon PDF. In the case of gluons, components of the gluon field strength tensor show up in the operator. We have also a gluon helicity PDF. For a spin 1/2 target, there is no gluon transversity PDF, which is forbidden because of angular momentum conservation. So the following two slides here, I will actually not say much about, give you the upshot. So on the one hand, on one of the previous slides, we said, here's a Parton model result. And you make a couple of assumptions, and then you can write down that expression that we have. And then on the other hand, I'm emphasizing I want to work with this piece here of the correlator. And how do these two pictures mesh with each other? And the reason, or you can actually see relatively quickly that you get the exact same result of the Parton model if you start with a correlator language. If you work with a correlator, so we have this famous handbag diagram, and you have a loop integral. K would be the loop. And in order to recover the Parton model result, all that you have to do is, in the upper part of the diagram, keep only the large component, K plus, and neglect K minus and the equilibrium. These are the Parton model approximations you have to make. And then if you go through the calculation, and the slides are uploaded, so you can go through that. It's not too complicated. If you've never done that, I encourage you to do that. And if there are questions, please come and see me. You get literally exactly the Parton. So that's number one. So the correlator language is not one thing which lives here, and the Parton model is something totally different. They are one-to-one connected. And the second point I want to make here is, I said before, we have this bilocal quark operator, and we somehow need this Wilson line in between to get color gauge invariance. And it almost sounds as if I have to put it in by hand. In fact, physics provides it for me. If we look again at the handbag diagram, and I take into account the rescattering of the struck quark with remnants of the target, more precisely, summing up contributions of longitudinally polarized gluons to all orders, you literally generate here this path order expression. It turns out, so in general, if we have a Wilson line, it's a line integral, let's say from A to B, which can in principle go along an arbitrary path from A to B. But in the derivation of factorization, it turns out that for the PDFs, you are connecting these 2 points of the quark fields with a straight line. And then what is often done, and therefore many people actually don't know about that here, is you use a light cone gauge, A plus equals 0, in which this Wilson line reduces to the identity operator, and you no longer talk about that. But in a general gauge, you have basically this object here. So in physics terms, again, the Wilson line is generated by the final state interaction of the struck quark. And these effects play, some of you may know that, an extremely important role in the context of TMD physics. All right, so last two slides, and before I move on to the TMDs, I think you have seen many plots on PDFs. I picked here just once. So there's a few groups in the world who lead the way. One of them is this NNPDF collaboration. Here results for the unpolarized PDFs, for the up balance distribution here in red and the down balance in blue. You know the definition of valence quarks is quark minus anti-quark. This distribution can be integrated over X. What do you get if you integrate the up valence distribution over X for the proton? 2, yes. So you get basically by definition the number of valence quarks. For the down equals 1. What do you get if you integrate the up distribution over X? Infinity. The number of quarks, so this is quark density modulo the caveats that we said. And if you integrate it over this, you would basically count the number of quarks. But because of the small x behavior, this integral doesn't exist. So out of these distributions here, it's only the red and the blue one where you can carry out the integral. All the others, the integral does not exist. And if you go to somewhat smaller x here, the gluon immediately dominates here, and then you have here u bar, d bar, and strangeness having somewhat similar behavior. And here we have from another collaboration the corresponding thing for the helicity PDFs. And one qualitative thing to take away is that the helicity PDFs have somewhat larger uncertainties, especially once you go to somewhat smaller x. And this is one of the areas where people think the electron-ion collider. So the very last slide on the PDFs is the following. What can we do with this? Well, it's nice that it's PDFs, but we can, for instance, calculate momentum fractions. So as I emphasized before, for most of the functions, the lowest moment doesn't exist, but the second moment does exist. And the second moment has a physics interpretation of a momentum fraction carried by a certain parton. And specifically in the case of a quark of quark flavor Q, we carry out the integral from -1 to +1. The region from -1 to 0 is by definition the anti-quark contribution for that quark flavor, and that is what we call then the average XQ. Here's a definition for the gluon. These depend also on the renormalization scale. If you sum them up, you get 1. This is a scale-independent result. So that is a robust result. You can actually use a scheme, whatever you want, you always have to get. So, and here are some numbers for mu squared equals 4. It's the same set of PDFs we saw on the previous slide, according to which we have about 35% momentum is carried by the up quark, about 40% by the gluon, close to 20% by the down. And here's added the contribution from strangeness and charm. It's about 6%. And if we go to a higher scale of 10,000 GeV squared, the up quark number goes down quite a bit. The down quark goes down. The heavier quarks play more in the role. Here, bottom has to be taken into account. Top is not yet active yet, and the gluon goes also somewhat up. It's actually interesting to compare those numbers here at the scale of 10,000 GeV squared with numbers that one can derive rigorously, which are asymptotic momentum. It's an exact result, which says if the scale goes to infinity, about 47% of the momentum should be carried by the gluon. If you look at this, we're already very close to that for the gluon. However, for the quarks here, we're still far away from each quark in that limit carries about 9% of the momentum, including the top, which is not yet active here at this scale. So we still have to go to quite a bit higher scale in order to, oops. Oh, I already. We have to go to higher scale, basically. All right, so probably used way too much time. We started at quarter
Yes,
past, right, or 20 past or something like that. All right. So now we have prepared the ground, we have prepared the rotation, and now everything goes easy, smoothly. So we switch now from PDFs to TMDs, and I emphasize again, this discussion here, I didn't change anything compared to the only thing is I didn't write again this correlator here in Dirac space. I just wrote right away the one where we do the projection. And now, if we want to define TMDs, what is the same as for PDFs, we put the momentum transfer delta to 0, the exact same thing. We always call K plus equals X times P plus. And the difference is we are not integrating over K minus and K perp, but we're only integrating over K minus. And as a result, this object depends on both X and K perp. So that's the main difference. And because of that, since we don't integrate over K perp, we don't have here C perp equals 0. So we have again a bilocal quark operator sandwiched between the same momentum states. But these two quark fields are now not just separated along the light cone, but they also separated in the transverse. And that may not seem very dramatic. However, it makes really the mathematics very different for these objects compared to the. So we're already ready and we can show the full list of leading quark theorems. Here they are. It's dying.
Oh, I was told that you need to shake it. Sorry.
But it's one of those high power things can work for half an hour. So now we use the same projections that we have seen before, gamma plus, gamma plus, gamma 5, and this here. No change. And now we have two terms here. The first one is, again, the unpolarized PDF, but now it depends on X and the transverse momentum. In fact, it doesn't depend on the orientation of the momentum, but just on the magnitude, put differently, K perp squared. And the presence of the K perp allows us to write down this structure. This looks a little cryptic here. This epsilon perp is a two-dimensional epsilon tensor. If you write this out, the numerator is nothing but the third component, cross product of K perp in this tree. There's no big deal here with this mass. This is just introduced so that the entire prefactor here is established. And this structure is then multiplied with what we call the Sivers function. Moving on to this case, gamma plus gamma 5, we have now the transverse momentum dependent elicity distribution and another structure multiplied with another TMD. And in the third case, we have the transverse momentum dependent transversity, and we are able to write down actually 3 more structures. So if you add this up, we have a total of 8 leading quark. And let me right away say we have the same number for gluons. I'm not spelling this out here. Again, this decomposition follows from parity hermiticity, and there's a non-trivial constraint from time reversal, which is not related to the number of these functions, but to something we get to either today or tomorrow. And at this point, I hope to be able to come back towards the end of today's lecture, at least a little bit. These TMDs depend on 2 scales. Not just on mu, which is related to ultraviolet divergences, but there's another scale because we have so-called rapidity divergences. Is there anyone here in the room who has never heard this term rapidity divergence? And those who have heard it, is there anyone brave and tries to explain what it means?
Parameterizing the boost.
Parameterizing what?
Parameterizing the boost of the target.
It's not about parameterization. Oh, sorry. So when you think in terms of these light cone variables, so we said we have K plus, K minus, and K perp. Ultraviolet divergences, when you work with these variables, arise from a K perp integral as K perp goes to infinity. In contrast, and there you can take care of them using standard MS bar stuff, dimensional regularization. Rapidity divergences arise if you take the ratio of the plus and the minus component of the loop momentum, and if this ratio goes either to infinity or zero. And if in this limit, you run into a divergence. These divergences, as a matter of principle, cannot be regulated with standard dimensional regularization. And there's different recipes out there how people do that. This is a little bit of field in its own. We cannot get it. Anyway, again, I hope I have time at the end of the lecture today to say a little more about that and also about the evolution in these cases. All right. So quark TMDs have names. Sivers function, F1T perp, Bohr-Mulder's function, H1 perp. Then we have what often is called the Wormgear function. These two, Wormgear because the hadron polarization and quark polarization are perpendicular. Sometimes this is also, at least this one here is also called Kotzinian-Mulder's function because they used this in the early days of the field. And then finally, a name here which I personally never liked, pretzelosity. It's a bit slow. Anyway. And the reason why it's called pretzelosity is the following. The structure in front of this H1T perp is a quaterbone structure. And so that's why people basically gave this name. So, and then you can put these TMDs in such a table here, where here we have the quark polarization, unpolarized, longitudinally, transversely polarized, the same here for the nucleon. Here's our unpolarized PDF. Then here the helicity TMD. Again, here you see the difference of two densities. Imagine the situation, the nucleon is polarized like that, and one of the densities is where the quark polarization points in the same direction as the nucleon polarization, and then minus the density where the quark polarization is actually just opposite to the nucleon polarization. And except for this one, all the other 7 here are differences of densities. Here we have the transversity and this pretzelosity thing. The Sivers function is unpolarized quarks in a transversely polarized nucleon. The counterpart, Bohr-Mulder's function, transversely polarized quarks in an unpolarized nucleon. And then here we have these Wormgear functions. And these 2 panels here are empty, and that's a consequence actually of parity. Now, whenever you show something like that, people may accuse you of stamp collecting. We have so many functions, and maybe, but we should be mindful here. We have many areas in science where we have many more stamps. If you think, for instance, of the periodic table, no one would say we can just get rid of one. Why? Because the physics and the chemistry of each of them is unique. And in the same way, we have to keep in mind the physics of all of these TMDs is unique, and we should try to understand it as much as possible. Let me skip over that here, and let's now get to process which TMDs can principally be measured. The first one here is a flagship process, will also be a flagship process for the EIC, semi-inclusive deep inelastic scattering, or CDIS. It's the same as inclusive DAS, but now we are detecting, in addition to the electron in the final state, or the lepton, one hadron. In general, this process is gone. today. So in general, the process is described by 6 variables, q squared and xb we have seen before. Then in a case, if the target has a transverse polarization, that's an azimuthal angle, describing the orientation of that spin vector here relative to the lepton plane. And then we have one hadron in the final state, and each particle gives 3 variables. And they are typically denoted like this. CH, PH is the formula of the hadron. This CH essentially describes the longitudinal momentum of the hadron as a transverse momentum, PH per, and the orientation of the transverse momentum indicated by this angle. All right, so this looks pretty messy. So we look at semi-inclusive GAS, and we consider the following case. We consider unpolarized incoming leptons, but also longitudinally polarized ones, and on the target side, unpolarized, longitudinally polarized, and transversely polarized. And then in the one photon exchange approximation, you can actually decompose the cross-section. It's a model-independent result in terms of a total of 18 structure functions. 8 of them have been spelled out here explicitly. And they depend, each of them depends on 4 variables, xb, xbarc and zh, the transverse hadron momentum, and q squared. If we are interested in the cross-section as a function of the transverse momentum of the hadron for low transverse momenta, it is exactly these 8 here which give the dominant contribution. I will come back to them in a moment. So let's now take a closer look at the inner workings of that process. So we have, again, like in inclusive DAS, electron or lepton scattering of a quark, and then this struck quark here fragments into a hadron and unobserved stuff. This is at the amplitude level. We square that, we get then this representation of the cross-section. And now, in this case, the cross-section has 3 components. It has a perturbative part, which is like before, the lepton is not shown yet, but it's a lepton-quark interaction. Then it has this lower part here is our quark correlator that we have seen several times now, this phi. And then we have another non-perturbative object, the upper part here, describing the fragmentation of a parton into a hadron. And often people denote this so correlated delta. If you now try to analyze the CTIS process, theoretically, people distinguish 3 cases. The first one here is we look at the cross-section integrated over the transverse momentum. The second one is we keep it differential in the transverse momentum, but the transverse momentum of the same order as the hard scale of the process, which is Q. And the third one is the one we are interested in, differential in the transverse momentum, and that transverse momentum small compared to Q. If you look at the cross-section as a function of the transverse momentum, it is the last region where the bulk of the cross-section is sitting. And this is also the rear arm of the TMDs. In this case, you are sensitive to the transverse momentum of that quark relative to the incoming nucleon, and also sensitive to the relative transverse momentum between the fragmenting quark and the outgoing hadron. So that's the rear arm of TMDs. And I will skip this here, but again, you have this slide. This is try to summarize which approximations you have to make to get what people call the TMD parton model, similar to what we do for the ordinary PDFs. If you look at this on the slides, you have any questions, you can definitely contact me. I just want to save a little bit of time and right away go to the results for the structure functions. Here are actually the 8 ones that we saw, the list before. This FUUT contains the unpolarized transverse momentum dependent parton distribution, quark flavor Q, and the unpolarized transverse momentum dependent fragmentation function, quark flavor Q going into a hadron. And these 2 transverse momenta get actually convoluted through this delta function. And the reason why we have this convolution is this delta function expresses nothing but conservation of transverse momentum at this vertex. And then if you look at this, you see, well, here we have one case where the TMD PDF goes with this D1, and we have another one here, the G1, the Sivers function also, and this G1 T perp. So we have 4 instances where a TMD couples to the unpolarized fragmentation function. And if you look at the full list, there are these 4 TMDs with an H. They all couple to another function, which is capital H1 perp, which is the Collins fragmentation function describing the fragmentation of a transversely polarized quark into an unpolarized hadron. Remarkably, this is a non-trivial result. All of the 8 TMDs can be studied exactly once, and all of these structure functions have been measured. And so what people consider or have considered as the most important case is FUUT, because this is kind of the unpolarized cross-section, then the Sivers effect here, Sivers function multiplying D1, and the Collins effect, because this is very important handle on this transversity. But see, this is not the end of the story, by no means. And that is a very important point for TMDs. There's a whole ton of processes in which they show up. And one of them here, classic process, is a Trellian collision of 2 hadrons, and you produce a dilepton pair. And in the Parton model, you have this configuration here, quark, antiquark, annihilated to time-like virtual photon, then decays in lepton, antilepton. And if you look at the cross-section differential in the transverse momentum of the dilepton pair, you are sensitive to a TMD Parton distribution here and also here. And likewise, the same thing applies on the fragmentation side. If you collide a plus and minus, and you look at 2 almost back-to-back hadrons, you are basically sensitive to 2 transverse momentum-dependent fragmentation functions here and here. This is what these 3 processes were classically mostly discussed, but there's much more. And this even is not a complete list, and some of them can and probably will at some point also be studied at the Electron-Ion Collider because they are related to lepton collisions, but there's also a whole bunch for hadronic collisions. And some of you may have seen just last week, a paper came out where people extracted information on the transverse momentum-dependent gluon distribution based on Higgs production data at the LHC. So there's an extremely rich phenomenology. And even if you work in this field, given that we have so many functions and so many processes, it's sometimes not easy to keep actual track of all the developments that are ongoing. I think this fact that they just naturally show up in so many processes which can be measured is one of the driving factors. And let me discuss this. Let me show some results for data. This is historically, it's a pioneering measurement. I still remember well a conference in October 2003 where these results were first shown, a conference in Athens, in Greece. Pioneering measurement by the Hermes collaboration of Sivers and the Collins. This paper has, I think, close to 1,000 citations or something like that. And here is their results. These 2 panels for the Sivers effect, here is for the Collins effect. What they find for production of pi plus is a clearly non-zero result, about 5% or maybe up to 10% here. Pi minus Sivers effect is compatible with 0. Collins effect, pi plus, pi minus is both is non-zero. And needless to say, in the meantime, we have many more data, not only from Hermes, but also Compass, Jefferson Lab, not only for a proton target or hydrogen, but also deuterium, helium-3 in order to for the neutron. Let me skip over that and give just one other example. Historically, also extremely important. We talked about electron-positron annihilation into a pair of hadrons. And the cross-section not only contains this expected term, a product of two transverse momentum dependent unpolarized TMDs, but there is also a modulation which contains a product of two Collins fragmentation functions. And that is a very important object, remember, to extract the transversity. And here are pioneering data actually from the Bell collaboration. There's different ways how you can form asymmetries. I'm not going into that. Just mention that this has been achieved, and there's more data out there from Babar and also from Best. Let me now show a few results where people, without giving you the full QCD machinery, how people do that. I just want, I think in the interest of time, cannot do that if you want to give some sort of an overview. Here is two results from two groups for x times the unpolarized TMD F1U for these scales of 4GV squared at a fixed x of 0.1. The two of the main players in the field. The one is the MAP collaboration. They used Trillian data only in this work, and they used the neural network approach to quantify the error. The other one is Artemis. They used both Trillian and CDIS data, a more traditional way for quantifying the error. And within uncertainties, they agree. So, but you see the errors are still relatively large. If you remember these figures as a function of f. But of course, I mean, we have here another dimension. Before we had a one-dimensional function. Here we have two dimensions. Another example here, which I personally like very much, that's the extraction of the Sivers function by the Pavia group. It's basically the same, so to say, as the map that we saw previous slide. What is shown here in the left plot is actually this particular K perp moment of the Sivers function, red for the up quark, blue for the down quark. And you see they are almost equal in magnitude, but opposite in sign. And this is actually a nice agreement with a model-independent large NC prediction, which was made more than 20 years ago. This is a robust result coming from QCD. These predictions do not always work that well, but they give you a rough idea whether, let's say, the up quark is roughly the same as a down quark, or the up quark is roughly the same as a negative. And so what is shown here is the following. We have seen this before, the TMD correlator traced with a gamma plus containing these two terms, the unpolarized TMD, and this second term is a Sivers function, where I wrote this prefactor a little differently, not with this two-dimensional epsilon tensor. So this quantity here on the right-hand side is shown here for x of 0.1 for a certain scale. In the kx, ky plane, the nucleon polarization points up here. Imagine for a moment the situation that this Sivers term is actually not present. In this case, if we had just the unpolarized TMD, the maximum would be here at the center, and we would have total axial symmetry. And the presence of this term here does two things. It shifts the maximum away from the center for up quarks a little bit to the right, for down quarks to the left, and it distorts the axial symmetry. And what you can nicely see in the case of the down quark, this effect is larger than for the up quark. The reason is that the down quark Sivers function is as large as the up quark Sivers function. However, the down quark unpolarized PDF is smaller than the up quark unpolarized PDF. And the effect that we're seeing here is basically by how much this is shifted is the relative size between the Sivers and the unpolarized TMD, because both enter. And the third and the last one here is the for the transversity distribution, as we emphasized before, the transversity distribution, even though it's one of the three collinear ones, why do we discuss it in the context of TMDs? Because we need another chiral odd analyzer. And one of them is this Collins function. We talked about that. I wrote this. In fact, we have seen this before. It's written now differently. We have the transverse momentum dependent transversity times the Collins function. This is for single hadron production, but you can also do this for dihadron production. this has an advantage in the sense that you can use collinear factorization and you can right away get access to the X-dependent transversity distribution, but you're paying a price here. You need a fragmentation function for two hadrons, which have a non-trivial dependence on the invariant mass of the two hadrons, which is typically much more complicated than, let's say, the K-perp or P-perp dependence over here. Anyway, both have been, extracted. And so the light bands here is for single hadron production, for the up valence and the down valence. And the darker bands, full bands for the dihadron channel. Dihadron work was actually largely driven in numerics by one of my former students, Chris Kokusa. And what you see here is in arrows, you have actually kind of agreement. So my time is probably, oh, well, okay. Can I have 3-4 minutes? Because then I can just say a few words about TMD.
We have half an hour break after each lecture, so you can go into this.
No, I just want to get done with a couple of slides on TMD evolution. We will still tomorrow talk for, let's say, 10 minutes or so about TMDs and then move on. But I would like to get this discussed. It's a little sketchy, but I hope you get some sort of idea, at least of the physics coming out of it, without getting into all the complicated mathematics and details of Collins-Sober evolution equation and stuff like that. So, and because I'm very sketchy here, I'm not sketchy because this is not important. It's highly important for the field. However, it's also relatively technical. And if you want to read more, these are definitely good resources here. So as we said before, the TMDs need two auxiliary scales. The scale mu, like in the case of PDFs, shows up or is needed because we have ultraviolet divergences. In the case, the scale zeta, often called zeta, shows up because of rapidity divergences. And I already tried to explain a little bit the difference of the two. And as I said here, ultraviolet divergences, we can use DIMREG. For rapidity divergences, DIMREG changing the space-time dimension is not helpful. But you can, there's different regulators in use in the literature. It's not unique. This has certain complications, and one of them, which is definitely a qualitative result I want you to take away, is the following. If you have managed to introduce all these regulators to come up with a TMD, which is literally well-defined, which anyone can take, either a model calculator or someone in a lattice and say, I tell you, calculate this object in field order, and everything is well-defined. Once you have such a definition, the intuitive thing, which you would expect, integrating it does not give you the corresponding PDF. If you first regulate all these divergences and then you integrate over K-perp, you're not getting back to the integrated PDF. That's an important technical point that needs to be taken into account. I should also say that these rapidity divergences is in principle not something that is unique to TMDs. And if you want to study explicit calculations in a little more detail, I highly recommend this write-up here by John Collins from about 20 years ago, where he makes the following thing clear. If you calculate, for instance, in perturbative QCD, a TMD for a quark in a flow. So you have a quark and it emits a gluon. The gluon is a spectator. One move calculation. And you can calculate both in this QCD model. You can calculate PDFs, but you can also calculate TMDs. When you calculate the PDFs, you will see that individual diagrams show rapidity divergences. However, at the end of the day, you have to sum over all the diagrams. And in the case of PDFs, these rapidity divergences cancel between real and virtual diagrams, while in the case of TMDs, they don't. that's a qualitative difference. And it's not, again, even if you calculate PDFs, at the end of the day, there is no rapidity divergence, but at intermediate steps, the same divergence is shown. And you basically need to regulate stuff in the sense that then you add things and then you cancel the divergences and then you carry out the integral over the rapidity. All right, so last slide on that. Naively, one may think that we say, well, we have a mu dependence, like in the case of PDFs, but this mu dependence actually differs from the D-club evolution. It's not the exact evolution as we have for PDFs. The only mu dependence that we have here, for those who, let's say, are more expert in this, is related to the renormalization field. That's all what we have here. And the main driver actually is the zeta dependence that is covered by what we call a Collins-Soper evolution equation. And the unique feature of that TMD evolution is that in contrast to D-club evolution, there is also a non-perturbative component in that evolution. And people have really made a lot of effort to extract this so-called Collins-Soper evolution kernel, especially also the non-perturbative part, from A, data, and B, also from lattice QCD. There's remarkable progress. I do expect that next week, I know you have a couple of lectures on lattice QCD. I do expect that this is one of the important papers in that field that Sergey, I think, gives his lectures, will talk a little more. There's really a lot of progress in getting the coherent, let's say, phenomenology. So what does this evolution do? Again, I said I'm not going here in technical details, but I want to give you a sort of idea what the effect of that evolution is. And here I took some results from a paper which is about 15 years old. And they show two panels here. I'm not going in the details here. There's a dependence on a parameter which to some extent is free, which kind of distinguishes between where you start using perturbation theory and where you use non-perturbative stuff. That's not the main point, but just to say why we have two panels. Let's just look at one of the panels. So here, the full curve is for a scale of a square root of 2.4 GeV. I actually forgot why they used this odd number here. But anyway, and then the blue dashed curve is for Q of 5 GeV. And then the red curve is for the mass of the Z boson. And notice this is a logarithmic scale here. What you see is it's an unpolarized TMD. Once you go from lower to higher scales, then basically these distributions get wider. Or basically, so here we have, on the x-axis, we have K-perp. So overall, the maximum goes down, but then the effect spreads out to larger KT. This is the main thing which happens due to this Collins-Soper evolution. And the second thing, and I don't have a plot for that, people, of course, wondered what happens if you look at the Sivers asymmetry. And the Sivers asymmetry strictly means in the numerator, you have the Sivers function. In the denominator, you have this function. And both the Sivers function and the F1 evolve in a certain way. And the Sivers function has this extra prefactor of K-perp. There was this correlation K-perp, S-perp, et cetera, And this extra K-perp is generally leads to the fact that these asymmetries dilute. So not only do the individual TMDs get wider, but then if you have TMDs that have come with extra prefactors of K-perp, they dilute or get wider even faster. So that, for instance, and tomorrow I will briefly show a plot about that, if you look at the Sivers asymmetry in W boson production, which has been measured at RIC, if you calculate that with full glory TMD evolution, the effect is gone. While if at low energies for Hermes energies, we have seen 5 to 10%. But if you evolve that to a mass of the W boson, the effect is basic. And with this, I want to finish for today, if it's okay. Yeah.
So comments? Yes. Good.
I do have one just on question slide. On slide 12, with the transverse or the PDF, there was a bump in the gluon that are also around x equals 1/3. I was wondering if that has like any interesting physical meaning, I guess.
You mean in the here on the right-hand side?
Yes.
That's a good question. Ask Pavel tomorrow. I saw his briefly scan through his slides. Today he talked about unpolarized PDFs. I assume tomorrow he talks about helicity and transversity. I don't have a simple explanation for this behavior here, but it's all what I can say is people who do these extractions, I find it a little remarkable that the errors are so small here, but I have to take what we get from them. But I can just say this is what the data if I cannot say that there's generally we have a whole bunch of meaningful models on the quark sector which can capture many of the features of these distributions. However, for the gluons, this is much harder. So I don't think there's a simple model which could describe that feature. But again, ask Pavel to help you. You can tell him that I encourage you to ask that. Sorry, I don't have a good.
I'm just wondering, how are the momentum fractions per parton asymptotically calculated?
And that's a perturbative calculation. But you get basically this result already at 1. It's a very interesting result. You can do the same actually also for the total angular momentum in G spin-sum rule. We'll talk about this tomorrow. But we have seen that at least for the quarks, we are very, very far away from told you. But it's nice. We don't have so many rigorous results here, but it's nice to have such benchmark. Don't be shy.
Questions or comments? If you eat pretzel tonight, you should stare at it and think it looks like a protein.
Any feedback you can give me about the level can have an impact on what you will hear tomorrow.
You'll be here at 10:30 for discussion.